So let's start by going over the warm-up problem. I'm going to walk up to this integral and ask myself, is it algebra, trig, or a mixture of stuff? Well, here I've got a mixture of algebra and some trig, but I'm going to stop myself before I immediately go into integration by parts, because I'm always hoping for a u substitution first, which means I'm going to ask myself the question, does the derivative of one part equal the other part? And here the answer is yes. If I take this x cubed part and allow that to be equal to u, then my du, or my differential, is going to be 3x squared dx. And we almost have the 3x squared dx because I've got the x squared part and I've got the dx, just not the 3. I'll divide both sides by 3, and that 1/3 du is what I'm going to substitute for x squared dx. Now the other piece of this, because it's a definite integral, I'm going to want to make sure to change the bounds on that integral as well. This part, our textbook gives us two options for. One is to finish it off, plug the x's back in, and use the original limits. The other option is what I'm about to do, which is to include those limits in my translation vocabulary list. I'm going to come over here and say when x equals 0 and when x equals 1. When x equals 0, u is equal to 0 cubed. Conveniently, that's just 0. And when x equals 1, u is equal to 1 cubed. Conveniently, also equal to 1. That means I know my complete translation vocabulary list. When I translate this into u's, the 0 and 1 become u equals 0 and u equals 1. That x squared dx become 1/3 of du, and I'm choosing to put my 1/3 out in front. And then that cosine of x cubed turns into cosine of u. Next up, I'm looking for the antiderivative of cosine. That's going to be positive sine, and I'll get 1/3 sine of u going from 0 to 1. And again, because we've already changed our limits of integration, we just have to plug in the 1 and the 0. I'll have 1/3 sine of 1 minus 1/3 sine of 0. At this point, you're welcome to simplify this, but the only piece I would simplify is taking a minute to say that sine of 0 is 0. Sine of 1, I don't know what that is. You're going to reach for a calculator to plug that in anyway. Or if you're doing this on web work, you would just type that in as sine of 1. Next up, there was a question in the chat about doing some practice with logs. And there are two kinds of integrals that involve logs. One is if there's actually a log inside of my integral, and the other is where logs are going to be the answer to my integral. So we'll do a couple examples of each. For my first example, let me have natural log of x divided by x dx. I walk up to this integral. I say, is it algebra, trig, or a mixture of stuff? And this one happens to be a mixture of algebra and logs. But just like the last one, I'm going to pause before I go down the integration by parts road. Instead, I'm going to ask myself, does the derivative of one part equal the other part? And my answer here, once again, is yes. If I let u equal natural log of x, then du is 1 over x dx. And we talked about this a little bit on Monday. It is important to recognize and be able to think about whether something shows up as 1 over x dx or as dx over x. These are the same. So here, this dx that's kind of floating around at the back is technically getting multiplied by the numerator. And this x down here is sitting in the denominator, which means that is exactly what we have. And this turns into du. That other part becomes a square root of u. Before I find the antiderivative, I'm going to take one more step, which is to rewrite that as u to the 1/2 power. Now, we can use our rule with exponents. I'm going to add 1 to the exponent, divide by the new exponent. It's going to give me u to the 3/2 divided by 3/2 plus a constant. And now my last step, because this was an indefinite integral, I need to make sure to plug back in what the x's were. So if u was natural log of x, then that numerator becomes natural log of x raised to the 3/2 power. We have a choice for how to deal with that fraction down here, but dividing by 3/2 is the same as multiplying by 2/3. Well, when I walk up to this problem, it's just algebra, and I am never doing integration by parts if it's just algebra. So I'm hoping there's some kind of u substitution to make this look a little bit nicer. So I ask myself, does the derivative of one part equal the other part? And it's a little bit hard to see here, but I'm going to let that entire denominator be equal to u. When we do that, and I take my derivative, or my differential, then I get that du is 3dx. Well, I almost have a 3dx. I actually have a 5dx. So I'm going to do this in 2 steps. I'm going to take that 5 and pop it out in front of the integral. And over here, I'm just going to translate the dx. I'm going to go ahead and divide both sides by 3 so that I get 1/3 du is equal to dx. That means that when I rewrite this, that 5 is popping out in front of the integral. I'm going to go ahead and put that 1/3 out in front of the integral too, which means I'm left with 1/u du. When we find the antiderivative of this, it's like we're asking ourselves, whose derivative is equal to 1/u? Well, the answer, natural log. This one turns into 5/3 natural log absolute value of u plus a constant. Because I don't have limits of integration, this is an indefinite integral. And then for my last step, we're going to go ahead and substitute back in what u is equal to so that we're reporting our final answer in x's, just like how it was asked. It turns out that problems that look like this come up so often that it's worth kind of noting what the general form looks like. So anytime that I'm looking at the integral of 1 over essentially the equation of a line, right? 2 plus 3x, that's the equation of a line. I could even write that as mx plus b. Well, anytime I'm looking at something like this, where the m and the b are constants, this same sort of u substitution happens. We'll come off to the side. I'm going to let that entire denominator equal u, which means that my differential becomes m dx. And when I rearrange that, 1/m du is equal to dx. Translating this side, that turns into 1/m. Again, I choose to pull that constant out in front, times 1/u du, or 1/m, natural log absolute value of u plus c. And then final, once we plug everything back in, 1/m ln mx plus b plus a constant. Just one little note for web work here. It is important that we include those absolute value signs. And there are 2 ways to do that in web work. One is to use ABS and then put in parentheses whatever you wanted to be an absolute value. Or if you have a full keyboard, you can just use the vertical line key on your keyboard for that. The next problem that I want to do is another definite integral, but I want to tie it back to that idea that a definite integral represents some kind of area under the curve. So here's my function. I've got 1/x minus 2, and I want to find the area of the portion of this curve between 3 and 10 that's under the curve but above the axis. So as a definite integral, we know that we can write this as the definite integral from 3 to 10 of our function, 1 over x minus 2 dx. I'm going to give you a second to try this on your paper and get to a final answer. Great. Okay, so let's go through this together. A couple of options. We can just kind of remember that rule that we just did, because this has the form of 1 divided by the equation of a line. We can also do a u substitution, and that's the choice I'm going to make. If u is equal to x minus 2, then du is dx. And because it's a definite integral, I'm going to go ahead and change the bounds. When x equals 3, u would be equal to 3 minus 2, or 1. And when x is equal to 10, when I plug in 10, u would be 10 minus 2, or 8. Which means I can translate this into the same problem, essentially, but going from 1 to 8 of 1 over u du. I've been doing a bunch of these today. That is going to be natural log, absolute value of u. We don't have a plus c this time, and we've already changed the limits to go from 1 to 8. So I can think about this as natural log of 8 minus natural log of 1. Notice I did not include the absolute values down here because 8 and 1 are already positive numbers. By the way, natural log of 1, we could simplify that further because natural log of 1 is equal to 0. There was a question in the chat about whether we need to change the limits of integration. So I want to address that before we move on. Our textbook gives us 2 options. And the other option that our book gives us, and let's see, I'll squeeze this in. I'm just going to move my answer up here. Our answer was natural log of 8 minus natural log of 1. So the textbook gives us the option to leave the limits alone, but if we're going to do that, what we should remember to do is to specify that these were x values, not u. So x went from 3 to 10 originally, and then we can write in our u substitution, evaluate the integral to get natural log of u, and we'd have those limits of integration, but if we do it this way, because we know that these are things that we have to plug in for x, we have to take that extra step of plugging back in x minus 2 before we evaluate from 3 to 10. Now when we do that, we'd have natural log of 10 minus 2 minus natural log of 3 minus 2. And notice numerically, we end up in the same place. This is typically the mathematically preferred option, but in terms of would you have to do it this way on a test, either of these options should be fine. Okay, but what if I told you this isn't really the problem I wanted to talk about? I'm going to erase our alternate option down here. I didn't really want to find the area from 3 to 10. I actually wanted to find the area from 3 to 100. Well, in terms of our process, it doesn't actually change much. That would be a 10. I'd have to fix this because now when x is 100, u wouldn't be 8, it would be 98. And then I'd plug in a 98 over here and a 98 over here, and that would be a 98 in there. I don't know what natural log of 98 is, but it's some really big number. But what if I said I actually didn't want to go to 100? I wanted to go to 100,000 or 100 million. Or in fact, what if I wanted to find all of the area under the curve? I don't want to do it with this problem because there's just a little bit of messiness. So I'm going to switch our problem up so that we don't need a u substitution and get back to this general idea. So I'm going to do that, and I'm just going to turn that asymptote into my axis. There we go. And now I'm going to go from 1 to, well, I said that I wanted to go to 10 and then 100,000 and then, what did I say? 100 million. But for now, I'm just going to put in a placeholder, and I'm going to put in a placeholder of b. When we go to set up this integral as a definite integral, that means I'm integrating from 1 to b of 1 over x dx. And just using our integration techniques, we can finish this off because this is natural log absolute value of x from 1 to b. And then we can plug in and say that that's natural log of b minus natural log of 1. Sometimes we're not concerned with just finding the area from here to here. Maybe I want to find all of the area under this curve. Or thinking about some of those word problems and how definite integrals relate to word problems, this might look like I want to add up something. I want to add up some small rates of change forever, over all time. I want to add them up. So you can kind of imagine that there would be some instances where it would be important to be able to add this up forever. And the way that we do that is I think about taking that b, wherever the edge of my definite integral was, and pushing b out towards infinity. In 17b, we established a method for doing that, and that is to take the limit as b approaches infinity. Nothing changes about what we did. We just have this extra step now of after we've finished all of our sort of regular antiderivative stuff, now we're going to take the limit as b approaches infinity, which means in this case I'm going to end up with natural log of infinity minus natural log of 1. And natural log of infinity, that is headed to infinity, which means this overall answer is headed to infinity. And when that happens, when we've evaluated an improper integral, we call it improper because we have an infinity going on somewhere. When we've evaluated that improper integral, if the answer is infinite, then we say that it diverges. And that's the same language that we used back in 17a when we were talking about sequences and when we looked at the limit of a sequence. And if the limit of our sequence was infinite, we said that it diverged. But if our limit of the sequence came to a single number, then we would say that it converged. So let's do an example of one of these things, maybe that's going to converge. Going to be lazy again and reuse my graph by swapping that up there and calling that 1 over x squared. Well, if I go to find that same area, meaning I'm looking for the area from 1 to b of 1 over x squared dx, but I'm going to push that out to infinity. Well, this time, when I go to do that integral, this is not a natural log. We can take the 1 over x squared and rewrite that as x to the negative 2, which means when we find our antiderivative, we end up with x to the negative 1 divided by negative 1. And that's what's going from 1 to b. Well, when I plug in those bounds, I'm going to choose to rewrite this. Dividing by negative 1 just makes it negative, and x to the negative 1 means that our x could be written in the denominator instead. And then I'll be plugging in b and subtracting off, plugging in 1. And don't forget, I've still got that limit as b approaches infinity. Well, from this first piece, 1 divided by infinity, that's headed to 0. Minus a minus is going to make that a plus 1. So even though what we were looking at was finding this area from 1 all the way to infinity, the answer in the end is finite. We got a number. And because it's finite, we say that this converges. I'm going to pause for a second because that's weird. We just added up stuff from 1 to infinity, and it added up to a finite number. You don't have to think that's weird. Mathematicians happen to think it's really cool. And so don't be surprised when you're working through problems in this section or problems in web work that even when we're taking these limits that head to infinity, we often get numbers or values that are going to converge. So this is the last problem that we've got time for today. But this is often how we're going to see improper integrals presented to us, not just from a graph, but having been given some kind of definite integral where infinity is showing up in one of my bounds. So when I look at this, that infinity is my problem. This isn't a definite integral if I don't kind of have finite, if I don't have walls on it. By mathematical convention, when the infinity shows up at the bottom, we call it A. When it shows up at the top, we call it B. But it doesn't matter. It's an arbitrary choice. You could always use A or always use B. I'm going to choose to use A and say we're looking at the limit as A approaches negative infinity, A to 0, e to the negative x dx. Just like on the previous problem, I'm going to start by finding the antiderivative. And we could write out a u substitution here, but I'm not going to. I'm just going to remember for myself that anytime we're taking the integral of e to the kx dx, that antiderivative is 1 over k. K, I said k, I wrote x. 1 over k e to the kx plus c. In our case, that negative x, really it's the negative 1 out in front that's our k. Which means my antiderivative is 1 over negative 1 e to the negative x, and then we're going from a to 0. 1 divided by negative 1 just makes it negative. So I'm going to plug in things here. We've got our limit as a approaches negative infinity. When I plug in 0, I'll have negative e to the 0 minus negative e to the negative a. Well, e to the 0 is 1, so that we can deal with. So now I've got a negative 1, and minus a minus is going to make that plus, and then we've got e to the negative of a negative infinity. I know I threw lots of negatives in this. Well, a negative of a negative makes that positive again, and e to the positive infinity is headed to infinity. So this whole thing is headed to infinity. Because we didn't get a single finite number, we say that this thing also diverges.